Okay. So with these problems, I'm wanting you to develop some number sense with logarithms. And you can kind of remember that whatever the base you see on the logarithm, you're looking for what exponent on that number would give you 52. So ultimately what it is saying is that logarithm is the exponent on a base 2 that gives you an answer of 52. This entire expression that I'm putting in the box is this exponent. Logarithms are themselves exponents. So with that in mind, what we want to look at is maybe a table of the exponent and then what is 2 to the power of that exponent. So with 52, obviously, we don't want to start with 1. So let's start with 3. If the exponent is 3, 2 to the third power is going to give us 8. For 4, 2 to the fourth power is 16. And I'm keeping an eye out for the number 52. And I realize I may need to go a little ways to find it. But nicely with 2 to the power, you can just keep doubling. So when I hit 5, I double 16. 6, I double again, and then I go, oh, wait, 52. 52 is in between these two numbers. 52 is in between these two numbers when my exponent on a 2 is between 5 and 6. What I want you to be able to do is realize that the value of that logarithm is somewhere between the number 5 and the number 6. So again, the purpose of these problems is to help you establish a stronger number sense of what logarithms are numerically. And then you also wanted to see 22, so I'll go over to that, and then I'll continue to just do more problems as we go. Now, I want to tell you that 22 is not a problem I would put on the test. I consider it a challenge problem of if you can do this, you can do anything I throw your way. When we first work with this, I'm going to break up the division inside this logarithm as I'm expanding. So that means that I have log base 5 of, and I'm going to write the whole numerator. Then minus log base 5 of the entire denominator. If you see more quickly how to expand, feel free. But I'm just going to do this slowly so that it makes the most sense if you need the help. Now, as I look at this parentheses, I'm looking for all the multiplication of things. 125 is multiplying to x to the fourth. And then there's another multiplication of the cube root of y squared. So what I'm going to do is split this up expand this into 3 logarithms because of the multiplication. That means I have log base 5 of 125 plus log base 5 of x to the fourth plus log base 5 of the cube root of y squared. Then I have my minus sign. And I want to be a little extra cautious. And I'm going to put a big giant parentheses here. And then I'm going to focus on this logarithm and expand that logarithm inside this big bracket. What I see is inside this logarithm, there is a multiplication of two things. So I can expand it into two separate logarithms that are adding. That means that I have log base 5 of the first item that is multiplying plus log base 5 of the second item that is multiplying. Now I'm not done yet, but what I want to do next is distribute this subtraction over this bracket. So every factor of the numerator turns into a logarithm that is adding. Every factor of the denominator turns into a logarithm that is subtracting. If you feel comfortable going straight to this last line that I wrote, feel free to go straight there. But I wanted to make sure I didn't lose anyone by showing that progression. So now there's a little bit more I can do to expand. And I'm going to move this so that it's not in the way of other things, or other things aren't in the way of it. I've got to say, I love the ability to lasso. No! It let go of my lasso. I'm sad. I asked too much of it. I'm going to have to move it a little bit at a time then. Come on. There we go. Lag time is not always friendly. Okay, here we are. Now, we want to look at what we have here that is actually an exponent in each of these logarithms. 125 is 5 to what power? So you can simplify log base 5 of 125 to 3. I want you to know that on the test tomorrow, I'm not going to have you simplifying this far while you are in the middle of expanding. Plus, and I want you to recognize that you have an exponent here inside that logarithm, and I can expand by taking that exponent and bringing it outside the logarithm as multiplication. I don't need to write the dot, but I'm putting it there for emphasis. Now, you can rewrite the cube root of y squared, which I'm starting to realize is actually difficult to read the way I have it there. So that's a 2 under there. The cube root of y squared is y to the power of 2 divided by the index of the root 3. So y to the 2/3 is actually what's sitting in that logarithm. The exponent can multiply outside that logarithm. And when I pull it outside the logarithm, it's gone, and all I have left inside is the y. For the next piece, you can see that the exponent is 7, and you can multiply it outside the logarithm. And then for this last bit, you want to recognize that the square root of p is actually p to the power of 1/2, which means that you can take that 1/2 exponent and turn it into multiplication outside that logarithm. And the only thing left inside the logarithm at that point is the p. And then that is expanded. I will not give you a problem this difficult on the test, but I feel it's important in a practice test to make sure to really clarify or to really challenge you, because if you can do those, you're good. Okay, so I believe that's asking for number 24. So let's do number 24. And I want to see if I can make my pen be a little bit thinner. Yes, I can. Okay. So we just did going from a compressed logarithm to an expanded logarithm. Now we're going from expanded to compressed. And we're doing everything in the opposite order. The last thing we did when we were expanding was bring exponents out to be multiplication. So the first thing I'm looking for as I condense is multiplication outside that logarithm. That can turn into an exponent. Yep, I want to go there. And I bet it's going to stop doing that. Yes, I have to keep telling it to save. Okay, so 1/2 becomes the exponent on w. And if you leave it as 1/2, that's fine. It is the same thing as square root. So I'm going to put down that that's the same thing as the square root of w. And again, if you leave it as w to the 1/2, that is fine. Then I have this 5, and it becomes the exponent on the p that is inside the logarithm. And then this 3 becomes an exponent on the t. Now you have addition and then you have subtraction. If you're able to see it quickly, you can write it quickly. And what I'm going to do as I write this, I'm going to use the square root of w instead of w to the 1/2. So I'm going to clean this up a little bit for the sake of just having it written one time. Now, I'm going to do this in 2 steps. You can do it in 1 step if you see it. I have 2 logarithms that are adding. That means that I can multiply their insides when I condense. So I have a square root of w and a p to the 5th power. And then I've got the minus log base 4 of t cubed. Then when I'm dealing with condensing the subtraction, I'm going to turn that into division. So I have log base 4 of the numerator, square root of w times p to the 5th power. The denominator is t to the 3rd power. And let me point out that the order these two are being multiplied, it can be reversed. You can write the square root of w as w to the 1/2 instead, and that's all perfectly fine. You know you're condensed when there's nothing outside the logarithm and everything is inside the logarithm. And real quick, I will not be cruel, but I just want to point out to you that you can only do this if the bases are the same. So when I say I'm not going to be cruel, I mean I will give you the bases that are the same. I'm not going to throw a loop at you. But do know that that has to be the same in order to do this. Okay. Is there another particular problem that you know you would like to see done? And if you don't have a particular problem, then I can do... Okay, excellent. I want to make sure to cover a little bit of everything today. When you graph your logarithms, first look at the base of this logarithm is a number larger than 1. When you have a number larger than 1, then it's basically a logarithm that is growing. It's going up from left to right. It has an asymptote that is effective on the bottom end. So I'm looking for an asymptote over there on the right side of the y-axis heading down. No matter what the base is of the logarithm, the parent graph will go through x-intercept 1. A second point can be found by taking whatever the base number is, and if you plug it in, you get the understood exponent of 5, which is 1. Basically, when you plug the base of the logarithm into the logarithm, you will get y value 1. And then from there, just try to graph the best you can. In a parent graph for a logarithm, domain, range, and equation of asymptote are the same, regardless of whether you're dealing with a base larger than 1 or between 0 and 1. All three of these are the same. The domain does not include 0, and it's just the positive numbers that x is allowed to be. Everything is allowed to come out. So the range is negative infinity to positive infinity. And the asymptote is vertical. So it's x equals, and it's located at x equals 0. For B, I'm having the parent graph translate. When an operation is inside the function to the x, you're going to do the opposite operation to your x's. So you are going to, instead of subtracting 2, you're actually going to add 2 to the x's, which basically means you're going to translate right 3 units. When an operation occurs outside the function, you do that exact operation to the y values of the parent graph. So I'm going to add 1 to all of my y values on the parent. But what does that essentially mean? That means I'm moving everything up 1. Now, you've been doing this translating since for a while, years. So I don't want you to lose track of what you already understand. You already understand this translating motion. What I'm hoping to create for you is a bigger picture of when it happens inside the function to the x, the opposite operation is what you need to use on the x coordinates to see what that did to the parent graph. If the operation is outside the function, then you do that exact operation to the y coordinates of the graph, and that will tell you how that particular arithmetic affected the parent graph. And so take the points that you know from the parent graph, and I'm going to put those points down. These are the parent graph points, and I'm going to move each of them right 3 and up 1. So right 3 up 1, right 3 up 1. And also the vertical asymptote was at 0, but now it is moving right. You know what? I just realized something, which you may have realized already. I somehow changed 2 to 3. And I'm sure that was confusing you for a while, and I'm sorry. Yeah. Yeah, sometimes I make that silly human mistake of reading something and then writing something else. Darn being human. So let me go back to, you've got asymptote 2 points from the parent graph. And now the asymptote is moving right 2 units. So the asymptote is now going to be at x equals 2. It's not affected by the up and down movement. But now the individual points move right 2 up 1, right 2 up 1, and then draw. And I realize it's a little bit challenging to draw, especially on a computer screen if you're able to. Okay, now I want to point out that the range will be negative infinity to positive infinity for every log function consistently across the board. The horizontal shift or the horizontal translation affects the domain and the equation of the asymptote. So you look at where's that asymptote? That asymptote is at x equals 2. The domain begins just, not including 2, but for real numbers that start after 2 and go to infinity. All right, next is 30. And if I need to, I can come back and look at these. Okay. You need to know the parent graph cube root of x. The cube root of x goes through 3 important points, and they're the same points that x cubed goes through. 0, 0, 1, 1, -1, -1. X cubed reaches for the sky and the ground. So it's like vertically trying to reach out. The inverse of cube root reaches out sideways. And so by reaching out sideways, I want to emphasize that it's heading this way. Now, if you want to be more accurate, I'm not expecting it out of you. You can plot an additional point of the cube root of 8 is 2, and also the cube root of -8 is -2, just to help you get a better feel for where this graph is located. And then cube root is vertically steep at the origin, 0, 0. And from there, it's reaching sideways. In part B, we're taking that parent graph, and outside we're multiplying by 3. So my y values that I have, 0, 1, 2, and 0, and -1, -2, they are all multiplied by 3, but they keep the x coordinate. Now, 0 times 3 is still 0, but y coordinate 1 times 3 is now 3. Y coordinate -1 times 3 is now -3. Also, the y coordinate at 8 that was 2 is now 2 times 3. And for -8, it was -2, and now it is -2 times 3. And that gives you that it's vertically stretching it. When you multiply outside the function, it's vertically stretching. But it is still needing to look like it is trying to head sideways versus reaching quickly up and down. In part C, I'm taking that cube root of x that is multiplied by 3 and has already been stretched, and I am translating it. Inside with the x, I see +2. That means I'm going to move left 2. Outside of the function, I see -1. That means I'm going to go down 1. So I'm going to take the points that I have on my stretched graph in part B, and I'm just going to plot them to prep for moving them. There we go. Now, moving them, left 2, down 1. There's my center where it is vertically steep, and it is having kind of this shape to it. And then left 2, down 1. Left 2, down 1. Left 2, down 1. Left 2, down 1. Did I? No. I did mess that up, didn't I? Left 2, down 1. Was that the only one that I had? Okay, yeah, there we go. I'm only going through the red points. It is a shifted graph. And then there you go. Now, make sure you know when it comes to cube root, domain and range, just negate all real numbers. Everything's allowed in, everything's allowed out. The inflection point is the point that begins at the origin, which will not be affected by the stretching. It will still be the origin. It is only affected when you translate. And when I translated, I moved left 2, down 1. And so that moved that point from the center of 0, 0 to -2, -1. All right, 38 is next. And now we're on to solving log equations. I want to locate my equal sign, and on each side have either just a number or a condensed logarithm. On the left, I see that I have a logarithm that is already condensed, but on the right, I can condense. With that addition, the right side becomes log base 4 of multiply the insides. At that point, when you look at the left side equaling the right side, they're both log base 4 of something. So the log base 4s cancel each other out and leave their insides equal. Now, up until this point, everything was about log rules. At this point, it's going back to your ability to solve quadratic equations. And the left side is 2x plus 1. I need to multiply these two together. And you can always use box multiplication, so I'm going to go ahead and just write that down to make sure that I don't lose you on that. I'm multiplying x minus 3 times x plus 5. And then when I add everything in the box, I'm getting x squared, like terms, plus 2x minus 15. I need one side to equal 0 if I'm going to solve this equation. So I'm going to subtract the 2x from both sides. Ooh, that's convenient. They subtract themselves away. And subtract 1. Now, at this point, you have two options. You can factor and solve for the two factors, but since you have x written only once, you can also go about the process of isolating. I'm just going to go ahead with the factoring. You want to notice that you have a difference of squares, and a difference of squares factors into a pair of conjugates. In other words, one's addition, one's subtraction. And if it is set equal to 0, then you're solving for where any one of those factors is equal to 0. But it must be equal to 0 for this to work. And I'm getting to possible answers, but I do need to double check. I need to go back, and I began with these 3 insides of logarithms. To be a solution, the number has to make all three of these be positive numbers. I can see pretty quickly -4 is a problem. If I try to plug -4 into this x, I can see really quickly I've got a negative number. If it makes any one of those have a negative input, it's out. Then when I put in +4, I do get a positive number in there. Positive and positive. So the only solution is x equals 4. That is definitely a challenging problem due to what you have to do after you reach this point. I'm going to be careful with the test problems because I want to focus more on your ability to do the logarithms than your ability to work with quadratics, because we're going to do polynomials next, and with those, you're going to end up being tested with these quadratics at that point. Okay, so, whoop, out. Yeah.
When it said that it equals x equals -4 and 4, do you have to plug in -4 to see if it makes a negative?
You do have to plug it in to see if it makes a negative.
Okay.
It's not because it's a negative number. It's because when it goes in, it makes, and it in fact makes more. If I plug it in here, it's also going to create a problem with making negative. But it's all about the logarithm is only allowed to have positive numbers go in. That's the problem that creates extraneous.
Okay, where do I plug it in? Which equation?
So what you want to do is go back to the original equation and grab each expression that is in parentheses after a logarithm. And you're then testing each one individually. So with the -4, you are testing 2 times -4 plus 1. Is it positive? It is not positive. So because it is not positive, that alone says it's not a solution. But it happens again with over here. You separately take x minus 3, you plug in that -4 that you think is a solution, and you are getting a number that is not, I just wrote it backward. You are getting a number that is not positive. If it makes any one of those three not be a positive number, it's out. The only way it stays in is if it makes every single one of them positive. So when I go to check the 4, when I check the +4, I get yes. Greater than 0, good. Next. Plug in +4. Is that greater than 0? Yes. Good. Check the next one. Is that greater than 0? Yes. All three of them make positive numbers go in the logarithm. That means 4 definitely is not an extraneous solution. It is a solution. So I hope that, excuse me, I hope that clarified. And then, does anyone have a particular number you want me to go to? Otherwise, I will just pick a number to go to. But if you tell me something, I'll do it. I'm not getting anything in chat, so I would say 45 is definitely one of the harder problems. it's harder than what I would put on the test. I would give you more the level you see from the other ones with 41 through 44, just so you know. But I'll do 45 because it is the challenge problem. And if you can do the challenge problem, then you are very good to go. I want to identify the variable that I'm actually trying to isolate. That variable shows up one time. So what I'm trying to do is pick off the weakest operation in PEMDAS or PERMDAS order and get rid of it. And I want to clarify before I get going about who's strong and who's weak. So.
See, now it gets confusing because now you want to make this subtraction a division sign because of the logarithms.
I know. I realize that's an issue. And it's unfortunate. I guess it's just this class is definitely a harder math class. Anyway, I'm just going to keep going instead of talking. Blah, blah, blah. Okay, my variable x, it's immediately multiplied by 3, and then a 1 is added, but there is an understanding that this is a parentheses because it is sitting in an exponent with a base of 5. Because of that parentheses, that is solid. And you can't even get into that parentheses until you deal with who that parentheses is on, which is that 5. So with that said, you may want to look at this as a big giant piece of don't touch it. And then look at the operations that that box has. That box has multiplication and a subtraction. Between those, the weakest operation is the subtraction, or should I say addition / subtraction. And it's actually the issue of the 12 being add / subtracted onto the piece that bears the variable. That means that that 12 is what I'm going to deal with first. It's an addition, subtraction, weak operation. I'm subtracting 12 from both sides. Yeah. So that leaves me with then -2 times 5 to the 3x plus 1. And then over here, -162. And you might see it already, but now I have to deal with the multiplication because having this exponentiation is much stronger than a multiplication. So I'm going to divide both sides by -2. And then I'm going to have my 5 to the 3x plus 1. And on the other side, positive 81. So now what is very important is that you understand that there is a parentheses around that exponent. To get into that parentheses, I have to deal with what's outside of it first, and it's 5 to the power of something. This is where the logarithm has to come in, and it cannot come in sooner than this. Now the logarithm comes in, and if I'm going to go ahead and just do a log base 10. So I'm going to log base 10 both sides of this equation. And I'm not writing the 10 because it's understood if I don't write. Now, the base of this logarithm does not match the base of the exponential, so they don't get to cancel. But I have the rule of an entire exponent can come out and multiply. And when it comes out, it's no longer inside the logarithm, and now I have just the 5 inside the logarithm. And now I want to come back to the fact that this is still a parentheses. Before I can go inside of it, I need to take care of the multiplication of this number. So I'm going to divide both sides by log 5. And now I have the 3x plus 1 equaling log base 10 of 81 divided by log base 10 of 5. And now is when you want to get your calculator out. And with your calculator, you want to find the log of 81 and the log of 5. So let me grab my calculator. And with this particular, with your typical, I guess this is Microsoft Calculator. I'm pushing first log. Okay, no, I'm not. No. Stop. Clear. Okay. If you're using this particular calculator, actually this is good because I can show you the two issues. I need to go 81 and then log and write that down. I'm just going to leave it as 1.9. So I'm going to remember 1.9. Then next I need to go 5 log. And I'm getting, it rounds to 0.7. And then I'm just going to take those two numbers and divide them. If I'm using a like the Google calculator, so if I go to if I basically just look up calculator and I get this, I believe, let me see if this is the one that does it. Yeah. With this one, if you first push log and then you push the number that I've already forgotten what number it is, 81, it will automatically put that in. But what's beautiful is you can go parentheses and then divided by, and then keep going, log 5, and that is going to give you a correct answer. So that is going to be a calculator that is easier to use. Another option that you have is the Desmos. If you open up Desmos and you're not concerned about graphing, you just want to find a number, you can open up the keyboard and let me show a little bit farther over. When you open up functions, you're going to go to miscellaneous and you have the log function. You do have the base as well if you want to put that in, but I'm focusing on this. So log and then 81. I can end the parentheses and then put divided. And then again, function, miscellaneous, log, and 5. and it's going to tell me the number right there, 2.73. So make sure that you know how to use your calculator, have one that you practice with, and just use that one. Once you get that number, which I now forget what number it is, so let me check again. Where did it go? 2.73. Now I do my last steps of subtract 1 and then divide by 3. So I'm going to go back over to calculator. Yeah, I'll just do this. Subtract 1. But I need to do a really big parentheses here. Let's see if I, there we go. And then you get the answer. Okay. Before you go, we've got 4 minutes left. Do you need me to talk through more of these problems and record it and post it? And also, perhaps now, before you leave, I can also tell you what I will not be putting on the test now that we've gone this far. I'm not going to have you do this on the test. I have this on the practice test because I think it is very important to help you develop that understanding of what a logarithm is. But it will not be on the test. What I will put on the test for sure, you will definitely see problems like these on the test. So make sure you feel comfortable with those. I'm going to cross these out and tell you, you need to do them, but I will not put a problem like that on the test. I will definitely have expand condense, but I'm not going to make it as difficult as 22. I would say 24 is probably a little bit closer to difficult. I will definitely have you graph a logarithm. You've got a base 5 example, a base 10 example, a base 1/2 example. I will have you do an x cubed graphing and a cube root of x graphing, so make sure that you feel comfortable with those. But you know what? I'm going to tell you one thing you can take off your plate right now. I'm not going to give you a base between 0 and 1 to graph on a logarithm. I want to make sure that you feel comfortable with logarithms and graphing when you're dealing with a base that is greater than 1. You will only be asked to graph a logarithm and its not translation, transformations, and its transformations with a base greater than 1. Then x cubed and cube root x, so 3 graphs altogether with their transformations. Then solving log equations is definitely going to show up. However, I'm not going to go as far as making you deal with the quadratics here because you're going to end up being tested on that on your next test. And then make sure you know how to use a calculator to solve equations. And that's it. I realized that I didn't open the quiz for you, so I guess you lucked out and you don't have a quiz. No quiz at all. And did I see a hand for a question?
Yeah, that was an accident.
Okay. Okay, what?
Just telling her to go ahead.
Oh, okay. So then did you also have a question?
Oh, so the translation, it's not going to be like a translation for the graph where it's like +1 or -2 or anything like that. It's going to be like a transformation where it's like where you're changing the shape of it.
So yeah, and right now I'm still continuing to present that you're going to have the parent. Let me get a. You're going to have a parent graph, and then a stretching or compressing by multiplication division, and then a translation from the stretching, and have them in steps. Yeah, I will say that I might have not as much on there because there are 3 different graphs, and I may minimize how much I have you show with the transformations. So you're not necessarily going to do all of this in each problem, but I want them to each at least show up within the 3 graphs, if that makes sense. Okay, so any other questions? Is there anything that you would like me to make a video on from the practice test and post later to help you with your studying? Also, know that the best way you can practice for tomorrow's test is to go to Google Classroom, look at a blank copy, and see if you can do it correctly without looking at the answers right away, or without using the answers, but checking with your answers. Anyway, have fun studying. I do have to make a test that is doable in 1 hour, so yeah. I'm going to stop the video.